Here are the important terminologies related with an ellipse. So let us start one by one. First we have the center, that is center of an ellipse. So let us consider some ellipse here. Okay. We are considering the horizontally situated ellipse. Okay. Now by the center it means the point which is at the center of the whole figure. So clearly for the horizontal ellipse in standard position, the center is nothing but the origin. Okay. So 0, 0 is the center. Then foci, as we have seen in the derivation, we can call them as say S and S dash or S1 and S2, whichever way. So the foci are, as we have seen, they are present at AE, 0 and minus AE, 0. So they are just symmetrically opposite on x-axis. So therefore foci have coordinates plus or minus AE, 0. That's how we can write it in a combined way. Then vertices. Vertices are basically the end points of the extremities of the axis where the foci are lying. Okay, so we can denote these vertices as A and A dash. And since this distance from origin to the point A, we know that that is nothing but A. So clearly the coordinates of the right extremity is A, 0 and that of the left extremity is minus A, 0. So together we can write the vertices as plus or minus A, 0. Remember that the other two extremities are not called as the vertices. Okay, the vertices are only those extremities which are present on the same axis where the foci are lying. So that's the easy way to remember which are the vertices of the given ellipse. Moving on, we have the directrices. So here is the right directrix and here is the left directrix. You know that the directrix is present at x equal to A by E, as we have seen in the derivation, and there will be another directrix present on exactly opposite side symmetrically, so that is x equal to minus A by E. So therefore combined we can write the equation of directrices as x is equal to plus or minus A by E. Right. Let's go ahead. Alright, next we have major and minor axis of the ellipse. So once again here we have ellipse. Right. The major axis is the whole length between the two vertices of the ellipse. Clearly it is nothing but 2a, because we know individually the distance is a. Right. And the minor axis is the length between the other two extremities on y-axis. So that is nothing but 2b. So therefore for the horizontal ellipse, the length of major axis is 2a and length of minor axis is 2b. Right. Then we have latus rectum. Now latus rectum is that segment which is drawn from the vertex, drawn from the focus of the ellipse and perpendicular to the major axis of the ellipse. So therefore, suppose this is focus S, so drawn perpendicular to it is this particular segment, and let it cut the ellipse at points L and L dash. So this particular segment L dash is called as the latus rectum. Now we have to find out what are the coordinates of extremities of latus rectum as well as what is the length of the latus rectum itself. Okay, so let us do that derivation quickly. We know that the focus is at AE, 0, correct? So therefore if we consider the equation of the ellipse, that is x square upon a square plus y square upon b square equal to 1, putting x as nothing but AE, so therefore a square e square upon a square, this term will reduce to e square plus y square upon b square is equal to 1. So therefore we get y square is equal to b square into 1 minus e square, and from the derivation we know that 1 minus e square can be written as b square upon a square. That is what we had assumed as a b square while deriving the equation of the ellipse. So therefore we get b raised to 4 upon a square as y square. So therefore taking the square root, we have y is equal to plus or minus b square upon a. So the plus sign indicates the upper extremity and minus sign indicates the lower extremity of the latus rectum. Right. So clearly the coordinates of L, that is upper extremity, are AE comma b square upon a, and for L dash they are once again AE, because L and L dash both have the same x coordinate, but the y coordinate will be the negative. Alright, so therefore these are the extremities of latus rectum, and hence if you want to find out the length of the latus rectum, it is clear that the total distance is 2 times b square upon a. So therefore the length of latus rectum is given by 2b square upon a for this ellipse. Right. Then eccentricity E. Okay. For this particular ellipse, we have seen that in the derivation we had a stage where we had said b square is equal to a square into 1 minus e square. That means we had got an expression which is on right side and we called that expression to be b square. Okay, that's what we had renamed. So therefore based on this we can easily derive the formula for e square. Okay, so dividing by a square we get b square is equal to 1 minus e square. Right? So that gives us e square is equal to 1 minus b square upon a square. So therefore taking the square root and before that simplifying the terms, we get e is equal to root of a square minus b square whole upon a, because the square root will change a square to a. So this is the expression for eccentricity, that is root of a square minus b square whole upon a. Right. And lastly we have to consider the focal distances. So by focal distances it means the distance of any point on the ellipse from the focus of that ellipse. So basically since there are two foci, so it could mean two possible distances. Okay, let's see how to derive that. Suppose we have an ellipse here, this is the axis and these are the directrices. So x is equal to a by a. Now let's consider some generic point. Let's call it as x1, y1, and these are the foci a comma 0 and minus a comma 0. Let's call this as p. This is s and s dash. So focal distance basically means the distance between the point and the focus, and we have to consider both the foci. Okay, so we want to find out what is the expression for SP and what is the expression for S dash P. Let's first focus on SP. We know by the definition of eccentricity, the very fundamentals, if we consider the perpendicular distance of the point from the directrix, and let's call that as say PM, we know that SP is nothing but E times PM, because that's the definition of, it follows from the definition of eccentricity. So therefore that is equal to E into bracket. Okay, now what is PM? We have to consider what is this distance. If you observe, isn't that distance equal to the entire distance, which is A by E, minus the distance of point from the origin, that is nothing but its x coordinate, so that is minus x1. So therefore since E is always a positive number, we can take it inside the modulus and multiply both the terms. So therefore here we get A minus EX1. Okay, now for the other vertex, that is S dash, we will get the distance as, that is S dash P, we will get the distance as A plus EX1. Okay. Now since this quantity will be positive, we can remove the modulus sign also. So therefore the two distances are A plus or minus EX1. Okay. In case you get any negative answer, we can write the modulus. Now here we can quickly check, that is if you consider the two possible values, that is A plus EX1 and A minus EX1, If you add these two focal distances, the term ex1 gets cancelled and we get the answer as 2a. And we know that for any ellipse, a is constant. So therefore 2a is also a constant. Hence it means that the sum of focal distances of any point on the ellipse is always constant. And if you recollect, that was one of the definitions of the ellipse itself. Alright, so these are the different important terminologies, and now we will summarize all of these for both the orientations of ellipse, that is the horizontal ellipse, that is a greater than b, or the vertical ellipse, that is a less than b. So in the next few slides we will go through the values of these important parameters for both of these standard orientations of the ellipse.